Good morning, one and all. The guest of today's webinar, Honorable Minata Jebdane, Member, Managing Council, Raj Shikshan Samstha Satara, Principal of our college, Dr. Yanis Gaikwad, my colleagues and dear participants. I am here to introduce today's our first speaker, Professor Dr. KY Rajpure sir, who is going to talk on Bose Einstein Condensation. Professor Keshav Yashwant Rajpure is currently working as a professor in the Department of Physics and head of music CFC at Shivaji University, Kolhapur. He was born on 24 July 1971 in a small village of Satara district. He was the first ranker student throughout his academic career. He had completed BSc degree in physics at Raj Shikshan Samstha, Shrirampaur College, Lonan in 1992 with university first rank. So he was awarded with Professor Shirke Award, Warange Award and Swami Scholarship. Then he was a member of Shivaji University Student Council. In 1994, he successfully completed MSc Physics and secured Kukarni Jamblikar Award for having stood first in merit. He worked as a junior research fellow and senior research fellow under the guidance of Professor Dr. C.H. Bose and was awarded with PhD degree in 2000. He had qualified state eligibility test examination in physical sciences in 2002. Even though the result of the examination was only 0.1%, his interested research topics include thin film, solar cells, transparent conductive oxides, photoelectrochemistry, gas sensors, and photoelectrocatalysis. He was honored for his contribution in research work for awarding a life membership of Maharashtra Academy of Sciences at National Chemical Laboratory, Pune in 2015. Till now, he has published 211 research articles in reputed international journals and acquired 7,372 citations. H index of his publications is 51. He has successfully guided 14 PhD, 2 MPhil and 59 MSc students. Currently, 5 PhD scholars are working under his guidance. He participated in more than 50 national and international conferences and has organized most of the conferences organized by his department. He has published 5 books and filed 2 patents. He successfully completed 5 research projects worth 86 lakhs, which were funded by various funding agencies of central government. He was instrumental in establishing various facilities in PIFC, that is Physics Instrumentation Facility Center. So university has entrusted additional responsibilities of head of the Department of Physics University Science Instrumentation Center of Common Facility Center on him. Currently, he is working as a coordinator of SITE, Sophisticated Analytical Instrumentation Center Facility Center at Shivaji University. He is member of Board of Studies of Karnataka University, Dharwad, PC College, Baramati, Vivekananda College, Kolhapur, EKTE, Isalkaranji, JSPM Rajarshi Shahu College of Engineering, Sathode, Pune, and KBP College, Pandharpur. He is working as a PhD referee for various universities. He is member of Marathi Vigyan Parishad, Material Research Society of India, Semiconductor Society of India, Indian Physics Association, and Indian Association of Physics Teachers. Also, he is working on editorial boards of various research journals. With this brief introduction, I will stop here.
Thank you, sir. Now I request Professor KY Rajpure sir to share his views with us. Please, sir. And audience are requested to drop their questions in chat box during the presentation.
Good morning, one and all. First of all, uh, let me thank organizers, especially Management Council member of Rajya Shikshan Sanstha Satara, Honorable Minatai Jagdhane Madam, Principal and my colleague, Professor Dr. N.S. Gaikwad Sir, IQSC Coordinator, Bade Sir, Head of the Department of Physics, Shetty Sir, Secretary of the webinar, Vartha, and Coordinator, Dr. P.S. Jadhav Pawar, for having entrusted this opportunity to me to talk in front of you at the occasion of live webinar on recent perspective in modern physics, organized by RB Narayanrao Borawake College, Srirampur. The title of my talk, as is narrated by Dr. N.S. Gaikwad sir, Bose Einstein Condensation, and the other title is When Atoms Become Wave. So I will be talking on this topic, and I am from Shivaji University Kolhapur and working as a professor in Department of Physics, Shivaji University Kolhapur, also heading two departments, namely USIC and CFC of Shivaji University Kolhapur, and I am also working as a coordinator of Dist's SAFE Center, Sophisticated Analytical Instrumentation Facility Center of Shivaji University Kolhapur. And this is a very nice and beautiful campus of Shivaji University Kolhapur, and these peaks where we have very biodiversity and natural resources of waters on the university campus. So, Bose Einstein condensation when atoms becomes wave is the title of my talk. So we know there are various states of the matter: solid, liquid, gas, and plasma. Liquid and gas being fluids, they tend to flow. And recently means before 20 years or so, the new phase, plasma phase, fourth state of matter was invented, was investigated, which exists at very high temperature only. But as you decrease the temperature, the plasma gets converted into gas, gas gets converted into liquid, liquid gets converted into solid, and further if you decrease the temperature below room temperature, it is possible to achieve a new phase of matter, new state of matter, which is the fifth state of matter, called as Bose-Einstein condensation. Bose-Einstein condensation. So this state is more organized than other solids. I'm going to explain you. In case of Bose-Einstein condensate, the entropy is the least, while in case of plasma, it is the most disordered state. So this BC is the most ordered state of the solid. Of course, there are no restrictions or molecules or atoms to be in one particular energy state. And this BEC occurs in case of indistinguishable particles, and very similar to light amplification by stimulated emission of light amplification by stimulated emission of radiation lesser. We have the Bose-Einstein condensation in case of the coherent particles. Yeah. So this BEC study, it is a superposition of many topics. This you can suppose as an interdisciplinary topic, which covers atomic physics, laser, electromagnetism, statistical physics, low temperature physics, fluid dynamics, condensed matter physics, and optics. So for understanding Bose-Einstein condensation, the way in which this BH is achieved, the way in which atom behaves as a wave, you need to know many topics, or we need to understand the concepts from all these topics. We know the particles which exist in nature, they can be broadly classified into the distinguishable particles and indistinguishable particles. What I mean by particle, these particles are the particles having, or the objects having size of few microns or so. So these particles, they can be classified as a distinguishable particles, and these distinguishable particles, they can be described by, or the way in which these particles, they are distributed in a system, it is given by Maxwell-Boltzmann statistics or the classical statistics. But the another class, indistinguishable particles, which are fermions and bosons, the way in which they are distributed in the system, it is given by either FD statistics or the BE statistics. FD means Fermi-Dirac statistics and BE means Bose Einstein statistics. Here I have given a simple example of distribution of two particles in two states. So when we have two states, namely 0 and E, and you have two particles, then there are four possible combinations. One combination is either both particles, they are in the ground state, or both particles, they can be in the excited state, or we have one particle in the ground state, we have another particle in the excited state, and vice versa. So in this way, in case of distinguishable particles, we have four possible ways of distribution of particle in the state or in the system. But if you have indistinguishable particles, then we have only three arrangements. Either both particles, they can be in the ground state, or they can be in the excited state, or one particle in the excited state and one particle in the ground state. We cannot state which particle in the ground state and which particle, because the particles are indistinguishable. And we are going to see the phenomena of Bose Einstein condensation in case of indistinguishable particles, that is bosons. So the particles, if they are identical and indistinguishable, then they can be broadly classified into two groups, as I told. The two groups, they are fermions, which are named after the scientist Enrico Fermi, and they exhibit half integral spin, and they obey Pauli exclusion principle. And we know the Pauli exclusion principle. According to Pauli exclusion principle, no two particles in the state, in the system, they can't be in the same quantum state at the same time. But we have another class of particles called as bosons, and they are named after the Indian scientist Satyendranath Bose. They are called as bosons, and they have integral multiple spin. Fermions, they have half integral multiple spin, and bosons, they have integral multiple spin. And they are named after Indian scientist Satyendranath Bose, where it is possible to put large group of atoms in this single quantum state. So it is possible to have condensation in the same energy states, for example, ground state, in case of boson only, not in case of fermion. So, Government of India given the Padma Vibhushan Award in 1954 to Satyendranath Bose. So here I have shown the cartoon made for the fermions and bosons, just to show the difference between fermions and fermions. So these fermions, if we consider one step to be one energy state and one cartoon to be one fermion, then at a time, only one cartoon can sit on one state. So only one particle in the one state. But in case of bosons, bosons are free. Two bosons, they can sit on one state, or more than two bosons, or all bosons, they can sit in the one state or one state. And this is the phenomena of Bose Einstein condensation, which we are going to explain. So what are the bosons and particles? What are the examples of the bosons and fermions? Bosons, as you know, photons are the massless particles. This is the best example of the bosons. We have the gluons, we have phonons, and these are many examples of the bosons. And we have fermions. The examples are electron, muon, pion, kaon, proton, neutrons, all subatomic particles, all elementary particles, they are fermions. We know in case of a boson, the wave function, probability amplitude wave function is symmetric under the exchange of the coordinates of the two bosons, but it is antisymmetric under the exchange of two fermions. Let us see some historical background about this phenomena, Bose Einstein condensation. Satyendranath Bose, the Indian scientist who was working in one of the universities in Dhaka, then Bangladesh was a part of India. So he was working on black body radiation, and he was investigating the way in which the photons can be distributed in the system. So in 1924, he derived Planck's radiation law without any reference to the classical physics by using novel way of counting state. Just now in one of the previous slides, I showed the way in which we can count the number of possible ways in which two particles can be distributed in the two states. So he was working, and with the help of such method, probabilistic approach, he derived Planck's quantum law, and especially this term 1 upon e to the power of E by kt minus 1 term in the spectral energy density of the black body radiation in the Planck's radiation law. We know Planck's radiation law is very useful for the milestone in the physics study. This work was the work by Bose was restricted to the way in which photons were distributed in the system. He sent his work to the Einstein because his paper was not published by any Western magazine then. Therefore, what he decided to send his work to Einstein. What Einstein did, Einstein translated, he was convinced by the idea by Satyendranath Bose. He translated his paper in German and sent it to one of the journals, Z for Physics. And this paper was published. So, this is the letter sent by Satyendranath Bose, being unknown person to him. I have ventured to send you the accompanying article for your perusal and opinion. I am anxious to know what you think of it. I do not know sufficient German to translate the paper. If you think the paper worth publication, I shall be grateful if you arrange for this publication in the Z for Physics. Though a complete stranger to you, I do not feel any hesitation in making such a request, because we are all your pupils through profiting only by your teaching through your writings. Yours faithfully, Satyendranath Bose. So the idea was appreciated and accepted and convinced by the Einstein, and therefore he translated Bose paper into German and sent it to publication with his comment, with the covering that Bose deviation of the Planck's formula appears to me to be important step forward. The method used here gives also the quantum theory of the ideal gas. I shall show it elsewhere. So, the work by Bose was adapted by Einstein, and in this way, the Bose, he put forth the statistics for the photons, the particles which makes up light, and Einstein adapted the work by boson and for other bosonic particles and atoms. What was the idea? Idea was, at a finite temperature, at the least possible temperature, almost all particles in the bosonic system, they were specific about the system. They talked about the bosonic system. If you take the temperature of the bosonic system to lowest possible temperature, maybe near to absolute zero, then it would congregate in the ground state, where quantum wave functions of all particles start to overlap and atoms get locked into phase with each other and they lose their individual identity, and the phenomena of Bose Einstein condensation occurs. And this was the statement of Bose Einstein condensation, and therefore the both name Bose and Einstein, they come. So it is expected that all particles, they come in the ground state. So if you consider the state of the particles at room temperature, it is the high energy state because they have some velocity, they have some momentum, they have some energy, non-zero energy. So if somehow, if you make the energy of all these particles to be zero, means the momentum to be zero, means the individual velocities to be zero, somehow if it is possible to make all the system particles to be motionless, then only the phenomena of Bose Einstein condensation is possible. So here I have tried to show the particles and their motions and the wave functions. These individual wave functions, when they start to overlap and there is no difference in wave functions and the identity of individual particle, the phenomena of Bose-Einstein condensation takes place. The scales of the temperature that we used to be, for example, Celsius scale, Fahrenheit scale, or Kelvin scale, for example, Celsius scale and Fahrenheit scale, they have origin in our day-to-day perceptions, the phenomena of a day-to-day life. For example, 0 degree Celsius is the freezing point of water, and 100 degrees centigrade is the boiling point of water. And we divide this region between these two into 100 equal parts. Therefore, each part is called as 1 degree. Similarly, 0 degree Fahrenheit is the freezing point of saturated salt of water, and 100 degree Fahrenheit is the approximate human body temperature. Therefore, the region between these two is divided into 100 equal parts, and each part is called as 1 degree. And therefore, in this way, the Celsius and Fahrenheit scales were existed. But as I said, they were the perceptions from our day-to-day life. There was temperature below the perception of human being, below freezing point of water, below freezing point of saturated salt of water. And how that could be invented? That was invented with the help of the ideal gas equation PV is equal to RT. What they did for the known ideal gases, they plotted PV versus T, and it was observed that this PV versus T graph, when the PV product was extended on the temperature axis, it came to minus 273.50. So it should be on the temperature scale, the pressure becomes zero, energy will become zero, and that temperature corresponds to the absolute temperature, or it has the lowest minima, which is called as absolute zero. Therefore, they formulated a new scale where the temperature is not called as the degree Kelvin, only Kelvin. And therefore, on the Kelvin scale, we know the freezing point of water is around 273 and boiling point of water is around 373, and 300 K is approximately room temperature on the Kelvin scale. So there is an absolute lower possible temperature called as absolute zero. Absolute lower possible temperature than the freezing point of water and freezing point of saturated salt water. So the existence of absolute zero is a simple consequence of definition of temperature. Let us see how temperature can be defined. For that, let us consider a container, a glass in a closed container. Let us suppose we have a cubical container. We have two cubical containers. In one container, one gas, at other container, the same gas, but at lower temperature. Maybe at 0 degree centigrade and other at room temperature. If it were possible for you to see individual molecules and the way in which all these molecules, they are moving in three-dimensional container, cubical container, we would have certainly observed that the gas, which is at room temperature, which is relatively hot, then these gas molecules, they are moving in random directions with random velocities. At room temperature, they are jumping at very high speed. But if it were possible for you to see the cold atoms or the container, the gas container at 0 degree centigrade, what you could have observed, you could have observed that these cold gas molecules, they are moving systematically at relatively lower speed. If it were possible for you to find the average value of velocity in both cases, you would have observed that the average value is zero because there are few positive velocity, few negative velocity, and average comes out to be zero. But if you try to find the relative root mean square velocity, in both cases, you would have observed that in case of hot gas, the value of relative root mean square value, RMS value of velocity is certainly greater than the RMS value of the velocity in case of cold gas. So, in case of a hot gas, average root mean square value of velocity is higher. Here it is lower, means temperature is a measure of velocity fluctuation. How come? If you equate kinetic energy and the thermal energy with the simple relation half mv square is equal to 3 by 2 kt, we observe that V is given by square root of 3 kt by m, or V square is proportional to V square is proportional to T. So absolute temperature must by definition be larger than 0, because the relative root mean square of the velocity of the molecules of any system, they can't be 0 practically. And this binding, they are given by the third law of thermodynamics. We know it is possible to make the entropy of the system to be 0 at absolute 0. And we know it is not possible to achieve absolute 0. Therefore, it is not possible to achieve the entropy to be 0. So, this sets the stage for our discussion. So absolute 0 temperature is the 0 degree centigrade, 0 Fahrenheit, 0 K. So let us see the temperatures which we know. How cool nano K temperature could be. Let us begin our journey towards absolute 0. I have shown here logarithmic scale of the absolute temperature. So the important point, the beginning point is the 5000 K, which is approximately the temperature of surface of the sun. 2 order of temperature, or we come to very friendly temperature zone to the human being, where life exists. We know between 300 to 400 K, between the boiling point of water and melting point of freezing point of ice. And this is a very familiar temperature zone too. Moving below by 2 order of the temperature, we come to the point of 70 K. This is the freezing point of nitrogen, where the phenomenon of high tissue superconductor was invented. The word high I have highlighted by blue color, because though it is a very low temperature, it is called as high compared to the temperature which we are going to talk. We still move below by 2 orders of temperature and reach to the temperature 3K, where the phenomenon of superconductivity and superfluidity occurs. And this is a very extremely cold place. If we still travel below and think of temperature achieved by the Doppler cooling, then we go to few millikelvin. With this disperse cooling, we go to microkelvin. With the help of evaporative cooling, we go to few nanokelvin. Nanokelvin, but not absolute 0, but not still the 0 Kelvin. So now it is possible to cool atomic system to 1 million or even less than that. At this extreme temperature, the world at a utterly strange place, where our everyday common sense is useless, quantum physics rules, and with its contrary initiative laws, and atoms behave as wave. So the most unsettling aspect of the quantum mechanics is the wave-particle duality. We know the light has dual nature. It has wave nature, it has particle nature. Massless particles are there. They are called as phonons, we know. So it was a well-known concept, but the French prince de Broglie in 1924 realized that if the light has dual nature, the particle also should have the dual nature. It has particle nature and it should have wave nature. So with the help of Planck's and Einstein relation, E is equal to mc square is the Einstein relation, and E is equal to sc by lambda is the Planck relation. So with the help of these two relations, he established a new relation for the thermal de Broglie wavelength, lambda is equal to h by p, where h is the Planck's constant and p is the momentum. So as momentum increases, associated de Broglie wavelength decreases. And de Broglie proposed that matter is composed of wave, and he established the relation between de Broglie wavelength and the temperature with the help of a simple definition, or by equating the two energies, kinetic energy and the thermal energy. And he ended up with this relation. Lambda is inversely proportional to square root of temperature. So if you try to find out the de Broglie wavelength of helium at room temperature, for example, at 1 atmospheric pressure, we see that it is of the order of 10 to the power of minus 10 meter, very, very small. So the lesson which we take from this slide is that de Broglie wavelength is inversely proportional to square root of temperature. Means lower is the temperature, more is the de Broglie wavelength. This is the lesson which we take from this. So to understand why it is so useful to think of ultra-cold atoms as a wave, let us relate the de Broglie wavelength to temperature. So this is the relation between de Broglie wavelength and temperature, and it is inversely proportional to square root of temperature. And here also I have shown the temperature and de Broglie corresponding de Broglie wavelength for certain system on the logarithmic scale. So what we see at room temperature, for example, thermal de Broglie wavelength is very small. It is of the order of few angstrom or few nanometer. And if it is so, at room temperature, de Broglie wavelength, the wave exhibited by the particles, it has a wavelength of the order of angstrom or nanometer, then it is not possible for us to see the wave forming with the help of visible light. Whatever we see with the help of visible light. What we do, we shine a visible light on a particular object and the reflected light comes, and the visible light can resolve the details much smaller than its own wavelength. It cannot resolve, and therefore this wavelength is less than the wavelength of the visible light. So if you want to imagine or to see the particles becoming wave at room temperature, you need to use X-rays. Unfortunately, we know X-ray, they carry very tremendous amount of energy, and if we shine these X-ray to individual atom or the few atoms, they may destroy the atoms. Their energy of the order of 100 keV. That is the reason why at room temperature, the wave nature of the atom is normally irrelevant, and it is most useful to think of them as the particles at room temperature. But if you decrease the temperature to few nano Kelvin or so, 10 to the power of minus 9 K or so, the corresponding thermal de Broglie wavelength is of the order of 10 micron. And if you decrease the temperature to few microkelvin less, then thermal de Broglie wavelength is comparable to wavelength of visible light. And wavelength of visible light, we know it is 0.4 to 0.7 micrometer. So if you decrease the temperature, then certainly the thermal de Broglie wavelength of the atoms will increase, and with the help of visible light, it will be possible for us to see atoms really becoming a wave. That, and also we know that visible light can impede on the atom without destroying them, and therefore decrease the temperature of the system to see really atoms becoming the wave. And that is the reason why I have chosen the title of my topic as When Atoms Become Wave. If we decrease the temperature of the system, bosonic system, for example, Bose Einstein condensation is achieved. And once the Bose Einstein condensation is achieved, the atoms are becoming wave. And it is possible for us to see the atoms becoming wave. Let us see the well-known temperature, the naturally existing temperature around us. For example, how cold is the interstellar space? Interstellar space has the temperature of the order of 3 K. And this temperature was investigated by COBE satellite. COBE is the Cosmic Background Explorer satellite. And for this investigation, the NASA scientist Mather, he got 2006 Nobel Prize in Physics. So naturally existing temperature, lowest possible temperature, which is there, is the interstellar space 3 K. So you can take your system to the interstellar space and decrease the temperature up to 3 K. But at 3 K, we cannot observe atom becoming wave, or the Bose Einstein condensation cannot be achieved at 3 K. So what we do? We have the various techniques for cooling the atomic system. For example, we have cryogens like liquid helium or liquid nitrogen or other system based on these cryogens. We can take the temperature of this system to few millikelvin or so. But these conventional methods, they are insufficient to create the Bose Einstein condensation. But scientists, with the help of magnetic trap and evaporation system, they were able to achieve 20 nano K temperature in case of a system of 2000 rubidium atoms. And this was done with the help of atom light interaction. So, as I said, it was possible, or it is possible for us to see a particular object by shining light on it, visible light on it. This light itself provides a powerful and inexpensive tool to cool the atoms to extremely low temperature, up to 20 nanoK. So for that, let us simply assume the situation when we have an atom in the ground state. And if you shine this atom with the monochromatic light, whose energy is equal to or slightly greater than the difference between the ground state and excited state of this atom. So what will happen? This atom will absorb the photon, and this absorbed photon will take the electron from ground state to the excited state. So here, two physical phenomena that take place: law of conservation of energy and law of conservation of momentum. Law of conservation of energy requires that electron goes in the excited state, and law of conservation of momentum requires that the photon, it carries the momentum. It carries energy means carries the momentum. That momentum is being absorbed by the atom itself. So when a light photon is absorbed, the atom gets kicked in the forward direction. So two phenomena takes place. Atom goes in the excited state and atom get kicked in the forward direction. So when you observe the light which is coming out of the atom from other side, you see that it is less by one photon. So relatively less light comes out of from the other side. Now, if this electron will not remain in the excited state forever, after the lifetime of the excited state, it will again go to the ground state and it will emit the photon which is absorbed. And in this process, relatively more light will come out, and atom, because atom is removing its photon. So according to law of conservation of momentum, the atom will kick in the backward direction. In this case, very similar to back thrust, which is observed by shooting the gun. So in this process of absorption of a photon, absorption, emission, atom getting kicked in the forward direction and backward direction takes place. Now suppose the situation when system of atom is being illuminated by a light from all possible direction, then the phenomena of stimulated emission and spontaneous emission takes place. Even we shut down this light source, this spontaneous emission caused the atoms to get kicked in the random direction. So this atom light interaction is useful to understand the Doppler cooling, which I am going to explain in the next slide. So for that, let us understand, or let us consider the atom which is in the ground state and it is at rest, and we shine this atom by a monochromatic light from both sides, for example from left and from right, in two-dimensional picture scenario. So the energy of this light is chosen in such a way that it is slightly less than the excited state and ground state of this atom. So what will happen? This atom, it is shined from left with green light, shined from right from the green light. This atom will not absorb the photon because this energy is insufficient to take the atom to the excited state. So nothing will happen. But let us suppose that instead of stationary, the atom is relatively moving towards this left laser, and this same green laser is shining. But according to phenomena of Doppler effect I have shown, the pitch of the sound of the siren when the vehicle is approaching to you is continuously increases. In fact, it doesn't increase, but we feel that it increases, the pitch increases according to Doppler effect. So this atom will feel that this light is more blue means its energy is more than what it is, and therefore it will absorb photon and it will get kicked in the backward direction. And this atom will feel the light which is coming from the backward to be more red, means having less energy according to Doppler. Same thing happens when atom is moving in the other direction. So it will feel that the light which is coming from the forward direction is more blue, and the light which is coming from backward direction, it is more red. So atom will get kicked in the backward direction in this case. So let us assume the situation where we have illuminated the atomic system from 3 mutual perpendicular directions by 6 lasers, these atoms, they will absorb. And if you choose the radiation or the energy of this light laser such that it is equal to or slightly less than the energy difference between the ground state and excited state of the atom, then according to Doppler effect, this atom will get kicked from all the directions. But unfortunately, the atom gets kicked from all directions. The kinetic energy of motion is being stored in the form of potential energy. And this potential energy will further convert it into kinetic energy. So this is one of the disadvantages of the Doppler cooling, that we cannot completely stop the motion of the atoms. And therefore, this Doppler cooling has the limit, so-called limit, up to, we can cool the atomic system up to few microkelvin with the help of Doppler cooling due to random kicks. So for their discovery, for development of method to cool and trap the atoms with the laser light, in 1997, these 3 laureates, Chu, Donodi, and Phillips, they got the Nobel Prize in physics. So still at a few microkelvin, still it is not possible. We have seen on one of the graphs that it is not possible to achieve Bose Einstein condensation, and it is not possible for us to see atoms really behaving the wave as a wave. So we need to go further, and you go for another method below microkelvin. This is the Doppler limit. We need to have detailed understanding of the way in which the electron lose their energy. So by clever choice of electronic orbit and laser arrangement, it is possible to force the atoms to move in much similar way as the marbles which move on the corrugated roof. They move like this. They go up, they go down. They go up, they go down. While going up, their velocity is less. While coming down, their velocity is more. So we choose the atomic orbital in such a way that the atom is uphill and it loses most of the energy. And in this, so this phenomena is very similar to the motion of a Sisyphus in the Greek mythology, and therefore this technique is called as Sisyphus cooling. And with the help of Sisyphus cooling, we can decrease the temperature of the system still below than the Doppler cooling method, of the order of 10 to the power minus 6 K can be achieved with the help of Sisyphus cooling. But this microkelvin temperature also is not sufficient to achieve Bose Einstein condensation. So the method, which is very familiar, quite familiar to our day-to-day life, evaporative cooling. We know when cup of coffee or cup of tea, when you keep it on the table, with respect to time, the temperature of the cup of the coffee, it continuously decreases. The way in which this happens is the atom and environment interaction. The hot atoms, relatively hot atom of the cup of coffee, they will come on the surface. They will exchange their energy with the environmental molecules, and they will become cool and they will go down. And in this way, this will happen until there is an equilibrium between the liquid and the environment. So similar thing happens here. So what we do, we continuously decrease the height of the pitch or the magneto-optical trap or the imaginary vessel where the atoms are hold. So here I have tried to show, if we continuously decrease these imaginary walls of the container, the hot molecules which are zipping fast, they will fall off the pitch in the container, and what will remain? They will remain only the cool atoms. So this method is called as evaporative cooling. Therefore, in conjunction, in coupling with the Doppler cooling and evaporative cooling, it is possible to cool the atomic system to few nanodegree Kelvin, where the phenomena of Bose Einstein condensation takes place, and really we see the atoms behaving as the wave. So how they achieved the PEC? They heated the bosonic system, particularly sodium or the rubidium. They heated the system in the oven up to 350 degrees centigrade. They converted into vapor system, and in the path they put the laser light where the velocity was initially 300 meter per second. The velocity was decreased to 220 millimeter per second, and then this beam of atom, it was allowed to fall in the vacuum chamber called as MOT, magneto-optical trap, where there is a provision to illuminate this system central system by 3 mutually perpendicular laser systems, 6 mutually perpendicular lasers, and the magnetic field to control to hold the atomic system at the center. So it is possible to cool the rubidium, 1000 rubidium atoms to few nano K. The way in which this was done, the atoms were cooled by laser beams from all directions initially. Then they are confined by the laser beam and magnetic field. And evaporative cooling. After optical laser cooling, the light is turned off and the atom cloud is confined to the magnetic field. And in this way, Bose Einstein condensation was achieved. So this is an imagined picture of the magneto-optical trap where you can see the magnets. These are magnets, these are magnets. This is imagined picture. This is the photograph, very complicated apparatus they used, and you can see the one of the laureates, Ketterle, where sodium laser cooling system in 1992 experimental complexity can be seen in this slide. And this is the another equipment used by another laureate in 2001. So what must be the results of the Bose Einstein? Fine, they achieved the Bose Einstein condensation. As I told, they took the system to few nanodegree Kelvin, or they took their system to near to absolute zero. What next? How to see the atoms behaving well? So they monitored the velocity of individual molecules and they plotted the distribution function of this system. And we know the Maxwell distribution function or the Planck's radiation law, Planck's distribution function. So number of molecules, they are plotted against the velocity. And the velocity at the peak is called as most probable velocity. And we know there are the number of molecules with this velocity which are moving with that velocity, they are more in number. And the molecules which are moving with relatively less speed, they are falling on the other side. In case of hot gas, the distribution is relatively flat. If the temperature decreases, the distribution becomes narrow and peak-like. So these are the things which we take from the theory as far as the distribution is concerned. We have seen in case of Planck's radiation law, we have found most probable speed, average speed, and root mean square speed. So we are talking of a most probable speed. And this is two-dimensional representation of the distribution. This is the three-dimensional distribution. So we see the distribution as a dumbbell, right? So
sir, we cannot see the screen right now.
Hello.
Sir, we cannot see the screen. Screen sharing stop झाले sir. डी ब्रॉग्लीज वेवलेंथ पासून स्टॉप झाले. स्क्रीन शेअरिंग स्टॉप झाले सर तुमचं.
आता दिसते का?
नाही सर अजून.
स्क्रीन शेअरिंग थांबलेलं आहे, कोणी सांगितलं कसं काय नाही मला?
हा सर, डी ब्रॉग्लीज वेवलेंथ पासून बंद झालेलं आहे सर. त्यानंतरच्या डॉपलर इफेक्ट वगैरे स्क्रीन दिसलेलं नाहीये.
एक 2 मिनिटं गायकवाड सर, 1-2 मिनिटं.
हा
आता बघा. हॅलो, आता दिसतोय का स्क्रीन? हॅलो,
येस सर.
स्क्रीन दिसतोय का?
नो सर, अजून नाही सर.
अरे दिसतोय सर. दिसतोय सर.
दिसतोय.
याचा काय प्रॉब्लेम असेल?
नाही सगळ्यांना दिसतोय का स्क्रीन, मला सांगा.
हो सर. हो
हो सर.
हो सर.
ओके दिसतंय.
मी घाबरलो एकदम.
दिसतंय सर.
Okay, so Bose Einstein condensation results, they are shown in this slide. So these are not imagined picture or nothing. These are actual experimental results from the Colorado first rubidium Bose Einstein condensation results. I request all of you to mute their mics. I request all of you to mute your mics. So these are the another experimental results in the other lab, in the MIT lab in 1995. So what are the results? So before explaining what they have observed and what we can interpret from the BC results, what we can interpret from the BC results, let us discuss the equation of state of the ideal Bose gas. So we know the equation of state of ideal gas as a PV is equal to RT or PV is equal to NKT. So if you look at this equation, it is PV is equal to NKT. This is the first term, and next is PV is equal to NKT times this term. So this term decides the way in which this equation varies or changes at various temperatures. So if you decrease the temperature at room temperature at normal density of the gas, the contribution of this term is very, very small, and the even ideal Bose gas at room temperature behaves as ordinary classical gas. But if you decrease the temperature of the system to few nanokelvin or so, and the gas is sufficiently rarefied, then the contribution of this term is very large, and this equation has to be modified and has to be considered, or these terms has to be considered. So what happens when we decrease the temperature? So there is a temperature called as critical temperature. So we can divide the regions above critical temperature, at the critical temperature, and below critical temperature, and absolute zero. So above critical temperature, when you are here, for example, the number of particles in the excited state, number of bosons in the excited state, they are given by this equation. They are given in terms of temperature, where N is equal to N0 plus Ne, where N0 are the number of particles in the ground state, Ne are the number of particles in the excited state, and Tc is the critical temperature. So this T by Tc is equal to means this is the critical temperature. So above critical temperature, all particles are in the excited state, no particle in the ground state. So when you decrease the temperature below critical temperature, number of particles in the excited state decreases and number of particles in the ground state increases. And this happens up to absolute zero. At absolute zero temperature, all particles are in the ground state and no particle in the excited state. So this is the simple outcome of the Bose Einstein condensation and Bose Einstein distribution. And we can theoretically estimate the critical temperature for the system from this equation. For one particular system, this temperature comes out to be few nanokelvin. That is the reason why the laureates, they cooled the atomic system up to few nanokelvin, and they could see really atoms behaving the way. So let me explain the BEC results. So we have three graphs. The left picture, this is at a relatively higher temperature where you have broad distribution with smooth distribution decreasing from V is equal to 0, for example. And this is the distribution at temperature greater than the critical temperature. This, let us say, this is that critical temperature, middle one, where we have two distinct contributions. Few particles in the ground state, few particles in the excited state. So this you can consider as picture at the critical temperature. This between critical temperature and absolute zero, where few particles in the excited state and few particles in the ground state. And here, only all particles are in the ground state. Fine. So all particles, they were in the ground state, but still people did not observe, laureates did not observe the atom becoming wave. So what they did? So they have system of atoms all sitting in the ground state, all they are moving, they are not moving, they are motionless, because they have all their individual velocities, momentum and energy is zero. They are behaving like a slave, means they are locked in phase with the quantum wave functions. Quantum wave functions of all these atoms, they are overlapped. Means what? They are following, they are behaving in a group. They are behaving in a group. For example, if one goes to left, all other say follow him. They go left. They one go to right, all they go to right. So let us suppose that you have a small system of 2000 rubidium atom at very chill temperature, few nano K, 100 nano K or 20 nano K, for example. And now if you shine one of the atoms of the rubidium with the monochromatic light, such that the energy of this light is equal to or greater than the energy difference between ground state and excited state of this rubidium atom, then the one of the atom will go in the excited state, will get in the forward, kicked in the forward direction. Now this message will be received by the side by atoms. They will say that, oh, we have to move follow, we have to follow this atom, we have to go below. And all they will tend to go below. By the time this atom, central atom, which has absorbed the photon, will emit its photon and emit the light. And it will be kicked in the forward direction. It will come up. So in this way, the atom, one atom, it will perform up and down motion. And this signal will be given to the side by atoms. Side by atom will feel that we also should follow him. They will go down and they will come up, and this will form waves in the BEC. And this is not the imagined picture. You see, this is not the imagined picture of the condensate. This is the photograph of the condensate where the waves have created. And these waves, they traveled from one point to other point. Like the waves which we see while dropping two pebbles in the calm water. And there would form an interference if we simultaneously illuminate both or two parts of the condensate and allow them to mix. So the interference pattern will be formed if and only if all the atoms, they are coherent atom and they are in phase with each other. And it was observed by the laureates that really the interference pattern, Ketterle, this is the photograph of the pattern, interference pattern observed by the Ketterle. And this is the photograph of the two Bose Einstein condensate. They spread out and interference pattern has been formed. And this is signature of atoms becoming wave, and these waves were observed with the help of visible light, because wavelength of these waves, it was of the order of few micron, because size of this pitch is say 20 micron and the wavelength is say around 1 micron or so. So atoms becoming wave, this was the evidence. So with the help of one of the animation, I would like to show you the way in which we can imagine this phenomena of cooling the atom. So in a gas, we see each atom has its own velocity. All bosons, they are allowed to move, have the same energy in the same time. And you can see here, all bosons, they have different energies and they are moving like, and if you decrease the temperature, the atoms slow down their energies and their individual velocities, they are increasing. And you can see they are finding very difficult to move. The atoms, they exhibit now as a wave. And you can see, surprise, when all the atoms, they are in the ground state, you can see all atoms, they are becoming a wave. All the atoms, they are in the ground state. So very similar to light amplification by stimulated emission of radiation laser, we can have the atom lasers, because all atoms, they are in the same state. So if you try to get out the atoms which are in same phase, then atom, they will come out of the container pitch like a laser. And this is the photograph of the atom laser which was taken by the laureates. The atom laser is the device which generates an intense coherent beam of atoms through stimulated process. So this BEC was first achieved in 1995 in Zilla laboratory, and the apparatus now it has been shifted to Smithsonian Institution. I don't know right now where this apparatus is kept. And the size of the what you can say, the condensate was a 20 micron, very small. And in that 20 micron, they took a photograph of the waves. And the condensate was formed with the help of 2000 rubidium atom approximately. And why 2000? Initially they took few lakhs of the rubidium atom, but they lost many of the rubidium atom in evaporative cooling, because most of the rubidium atom which were having more energy, they fall out of the pitch. And therefore, and this, what was the time? This condensate lasts for 15 seconds, and within this 15 seconds they did all experiment, and few condensate they can last up to 3 minutes. So within these 3 minutes, you have to do all your experiment. Now people are thinking of creating the condensation, Bose Einstein condensation of the in the condensed matter physics. For example, magnon. We know magnon is the quantized spin wave. So we know all the spins of the waves of the atom, they have different energy. We have a spectrum of energy, but it was observed that they are quantized. Only few energies are allowed. So if it is possible for us to bring all magnon in the same energy state, then that will form a common quantum state for this magnon. And therefore, it was possible to bring all magnon in the same state, and therefore they claimed that the quasi-equilibrium magnon, they form Bose Einstein condensation at room temperature. So these are the studies which are currently going on. In Nature, this paper was published in 2006. This paper was published. They could observe the Bose-Einstein condensation in case of photons. We know photons, phonon, these also are the bosons. Bose-Einstein condensation occurs in case of bosons only. So photons also are the bosons. And in 2011, they reported the experiment which revealed Bose-Einstein condensation in case of photons also. They want to see the way in which photon behaves, the way in which few photons they interact with each other by decreasing the temperature. Even they observed Bose-Einstein condensation in space. In 2018, recently, at International Space Center, the cloud of the rubidium atom, it was cooled to 10th millionth of the degree, and they observed the condensation at the space. So it was a suitcase-sized device, and in case of rubidium and potassium, they observed the condensation. The atoms, they are stable for multiple seconds. They studied more detail. The experiment could also tackle ideas like Einstein's equivalence principle. So they want to study further the Einstein's equivalence principle by creating condensation in space. We know, you might have read in this corona pandemic, one of our Maharashtrian girl, Dr. Amruta Ghadge, who graduated from Mumbai University, did her MSc in Pune University, did her PhD from the Nottingham University. She recently created the condensation remotely by operating remotely her apparatus. She was at her house, it was in her room, and on computer remote system, she created the condenser. This was one of the flash news in the corona pandemic. They observed the Bose-Einstein condensation in case of a plasmonic polytronic system. We know plasmon is a quantum of plasma oscillation. We know plasma, equal number of positive and negative ions, and we know the plasma frequency. Plasma frequency is equal to square root of 4 pi n square upon m, where n is the carrier density, charge carrier density, m is the effective mass of the electron. And the plasma frequency is given by this. But this plasma, that doesn't occur, or they are moving, they are oscillating. They don't oscillate with every frequency. They oscillate only with few allowed frequency, and therefore the energy of this plasma is quantized. And this quantized plasma oscillation, or the plasma, is a quantum of a plasma oscillation. And this plasma, in the polyreturn, what is the polyreturn? Polariton are the interaction. These are also are quasi-particles, imaginary particles. Interaction of a photon with phonon. So they observed the Bose-Einstein condensation in case of a plasmon, photon, and polariton. And they had very, of course, I don't have detailed knowledge about, I have not looked into the results of this, but people are working on this also. What are the applications of Bose-Einstein condensation? Of course, this is a very new area, and just now I have listed few 4-5 current trends of research in Bose-Einstein condensation area. But these Bose-Einstein condensation, they are used in atom optics, atom lithography, atomic clock, and they are used to set fundamental standards. They are used in holograms, they are used in communication, and they are used in fundamental understanding of quantum mechanics and black holes. So there are a variety of applications, only few I have listed. Of course, so far as this field is concerned, there are various achievements. In 1938, they achieved the condensation in case of a helium. Of course, it was a Bose-Einstein condensation only because helium particles, we have helium-3 and helium-4. Helium-4 is a bosonic, helium-3 is fermionic. So in case of helium-4, they could achieve this helium system to very near to its critical temperature, and they observed the phenomena. Then in 1995, rubidium-87, Cornell and Weinman. In 1995, Kitterly. In case of a sodium, they achieved. So alkali metals, when they are ionized, these are actually fermionic system. They are converted into bosonic system. So bosonic system, they could convert. So for their study, for achievement of the Bose-Einstein condensation in dilute gases like alkali atoms, and their fundamental studies of the properties of the condensate, Cornell, Kitterly, and Weinman, they were awarded with the Nobel Prize in Physics in 2001. Even the magazine Science, the cover page of a magazine Science, it showed the molecules, Bose-Einstein condensates, and the molecule of the year. So this issue was honored by the, what you can say, the Bose-Einstein condensate. So far, we have studied the Bose-Einstein condensation in case of sodium or rubidium. They have studied the Bose-Einstein condensation of the molecular lithium. Few fermionic system was converted into bosonic system, and in case of fermionic system also, they achieved the Bose-Einstein condensation. These are the superfluid gases. So always we look for the bright side of life, even in this corona pandemic. I feel this is the occasion to dissipate the scientific knowledge and create curiosity among the researcher for the various topics of the modern physics. Of course, I have a different research career and I have research topic to address as well. But I thought I should explain to all my fellow colleagues and new budding researchers to explain this very important idea of Bose-Einstein condensation. So I request all the audience, if they have any questions, they can put in chat box so that coordinator they may ask the question, or they can directly ask me the question. So I take this opportunity to thank all the patient listeners and the organizers to give me this opportunity. Thank you very much.
Thank you, sir. Your presentation drew audience came and held their attention during your lecture. There are some questions from audience. On behalf of audience, I will ask them. The first question from audience: what happens at the critical temperature that leads to Bose-Einstein condensation?
So at critical temperature, Bose-Einstein condensation doesn't occur. It occurs at lowest possible temperature. So it is the beginning of the Bose-Einstein condensation. So at critical temperature, few atoms starts to go in the condensed phase. That is the answer.
Next question is: how is Bose-Einstein condensation different from plasma?
Bose-Einstein condensation?
How is Bose-Einstein condensate different from plasma?
Bose Einstein condensation and plasma, these are the two aspects as far as states of matter are concerned. One occurs at relatively higher temperature, other occurs at relatively lower temperature, which is one is most disordered state and one is most ordered state. This is the answer.
Next question is, what happens if we mix Bose-Einstein condensate with plasma?
If we
mix Bose-Einstein condensate with plasma.
This is actually irrelevant question because we cannot in principle mix plasma with Bose Einstein condensation because plasma occurs at high temperature and Bose Einstein condensation occurs at lower temperature, so we cannot mix them.
Next question is, Bose-Einstein condensation is in which space, either in momentum space or real space, and why?
It is in real space, and you can look at this in momentum space also, because these are our perceptions. Coordinate space and momentum space are our perception. Therefore, we can look at this condensate in any space. So it is our convenience.
Next question is, in BZ, how is the interaction of visible light take place with de Broglie wavelength of particles?
So I did not explain that aspect at length, because for that also I have one separate lecture. The way in which electromagnetic radiation interact with Bose-Einstein condensation, that is a very good question actually, because when Bose-Einstein condensation occurs, BC achieves, so all the atoms, they are in phase with each other. They have locked their with each other.
Thank you, sir, for your nice presentation as well as excellent discussion. Now, I will
Anybody, they can directly ask the question.
Hello, audience.
Audience, they can ask the question by unmuting them and starting their video. Because I like questions. Okay. If there are no questions, once again I take this opportunity to thank one of the fellow colleague and very dear friend and joint secretary, ex-joint secretary of Rajkin Samstha Satara, respected professor, principal Dr. N.S. Gaikwad sir, and Dr. Pragati Jadhav for making me available this opportunity to talk on the topic of my interest. Thank you very much.
Thank you. Now, I will introduce the next speaker, that is Professor V.N. Matesar. He did MSc as well as PhD from Shivaji University, Kolhapur. He got bypass fellowship from Department of Science and Technology, Government of India. He was K. Krishnan Research Associate at BRC Mumbai in 2003. Also, he got DSC Award of Young Researcher in 2004. He was fast track Young Scientist during 2006 to 2009. He was Young Associate of Maharashtra Academy of Sciences in year 2016. He got SN Sheshadri Award for Instrumentation in Physical Sciences for the year 2016 and awarded by same in 2018. His area of research is development of hot and cold plasma systems, material processing